Now you've got a circuit here, and we would like to analyze this circuit by using node voltage method. This circuit is given like that, means sources references are given, as you see here. This voltage source 40 volts independent voltage source reference is given, and this is a dependent voltage source reference is given. Also, which element, so that has been forgotten, for example, that IC should also be given. Now it is right time to tell you that if this is not given, that means this definition relation cannot be written. You've got to give the reference that IC as well. So put that reference should have been already given. I have forgotten it, but I'll show you. So this is what is given to you. When the circuit given to you, this is given to you. What you're going to do next, in order to write the Kirchhoff laws, you need references. So anytime you write the Kirchhoff voltage law, or current law equation, you need references. So we've got to choose references. Current references we normally chooses, and then we say the voltage reference, depending on that, should be determined according to passive sign convention. So let's do that now. We choose the element references, make it different color. That I made this one as red because this should already be given, I said. Now for the others, I choose this color. So passive sign convention, and this one according to passive sign convention is going to be this. Let's choose this one like that. Choose this one opposite around that way, and this one like that. And according to passive sign convention, it's going to be like that. So you cannot choose that reference as you like, because you've got to choose it according to that, because the voltage reference is given. Current reference should be chosen according to passive sign convention. I have chosen this one randomly because the reference already been given. There were no references already been given, so I have chosen this one. Once I have chosen this as a current reference, the voltage reference should be like that. That's plus and that's minus. So that's passive sign convention. That means if you know how you're going to connect the ammeter, then you automatically know how you're going to connect the voltmeters. That's voltage reference is given for that. Now, next things that we've got to do is, in this method, we are going to start with the Kirchhoff current law equations, independent ones. So we are going to write Kirchhoff current law equations for independent nodes. How many independent nodes do we have? Let's mark them. So this one is, make it different color. That is one node. That's the second node. That's the third node. That's the fourth node. And that's the fifth node. So 1, 2, 3, 4 elements connected to that fifth node. And we already know that one of the node is going to be a reference node or ground. I'm not going to write Kirchhoff current law equation for this node. Why is that? Because this current law equation is going to be a dependent equation. So we don't want to write dependent equation. We're going to write independent ones. So altogether, number of nodes are equal to 5. Independent ones is nd minus 1 equal to 4. So 4 equations, Kirchhoff current law equations that I'm going to write. That's the first step. These are going to be independent ones. That's the step 1. And then step 2, definition relations I'm going to use. Definition relations. And these relations, currents are going to be transferred to voltages. And then step 2. Step 3, element voltages transferred to node voltages. We said we are going to write node voltage analysis method that we are going to use, so we're going to end up with the node voltages. There is one problem. While we are using the definition relation, there could be some cases that we cannot use the definition relation and transfer the current to the voltage. In this case, we are going to write a supplementary equation. We know already this. So, having done that, we are ready now to write the Kirchhoff current law equations to step 1. So, make it color, the black color, and then write this. So, the first node, there are 2 elements connected to it. This element current, so let's put the number for the currents. That's I1, that's I2, I3, that's this IC, and that's I4, and that is I5. And that's going to be, so let's make this element clear now. So what type of element of this? So this element is dependent element, dependent source. Why it is dependent source? Because diamond shape. So it is dependent voltage source. Why it is dependent voltage source? Because the voltage reference given. Voltage reference given. So this dependent voltage source voltage depends on what? Depends on that current. So that current is this current. So that is a current controlled dependent voltage source. So definition relation, V current controlled voltage source is equal 8 times IC. That means whatever the color you have here multiplied with 8, you get the voltage of this element. So this element has a current. This is I current controlled voltage source current. Is not seen in that definition relation. That means if you know the voltage, you cannot say the current of this element by using the definition relation, because it is not seen in the definition relation. So we've got to pay attention to this. If you write ICCVS equal to 8IC, that means you made a mistake. So at the beginning, if you do this analysis, make what the definition of this dependent source is and what is unknown of this dependent source here. That helps you while writing the correct equations. So let's start from the first node. We are writing Kirchhoff current law equations. The first one, we've got 2 elements connected to it, and both of the elements currents are coming out of the node. Then the sign of these currents are going to be plus. So I1 plus I2 equal to 0. Current law equation is known. So the rule was this: if the element current is coming out of the node, the sign is positive. It is towards the node, it's going to be minus. For example, for this element, if you're going to write the first node Kirchhoff current law equations, sign is going to be positive because this arrow comes out of the node. If you are writing the same element current for the second node, it is coming towards the node, so it's going to be minus. So here it's going to be minus I2. So I'm writing this second node current equation now. I3 is coming out of the node plus I3, and this is coming out of the node plus IC equal to 0. The third one minus IC, because it is towards the node 3, and it is towards the node 3, that is I4 minus I4, and plus I5 because it is coming out of the node. So for the fourth node, that I5 is coming towards the node, it is minus I5, and this dependent source current is coming out of the node, so it is plus I current controlled voltage source current equal to 0. So that's the step 1. What about step 2? We're going to use definition relation and transfer these currents to voltages if possible. So I1 is the independent voltage source current. By the definition relation, I cannot transfer this current to voltage. So I'm going to keep it as it is, I1. What about I2? I2 is related to a resistor. So I can write this resistor current in terms of this resistor's voltage. So it's going to be now 1 over 2. That's the inverse of the resistor multiplied with V2. So remember that. I'll maybe clear so some area here, maybe here, definition relation. V equal R times E. That's definition relation for the resistor in general. So if you transfer the current to voltage, then it's going to be I is 1 over R times V. So this is what I have done here. So the sign was plus, so there's a plus here, equal to 0. So minus of this one, minus 1 over 2 V2, plus I3, this is another resistor, and resistance of this element is 10, so 1 over 10 V3. And IC is also a resistor. Resistance value is 1 over 5 VC equal to 0. So negative of this one is going to be minus 1 over 5 VC, and I4 is a resistor once again. Sign is minus 1 over 20 V4, and this resistor is sign is plus, resistance value 1 over the resistance value 2 V5 is equal to 0. I have done this. What I have done, replace the current with the voltages by using the definition relation. So this is going to be negative of this, minus 1 over 2 V5. For this one, I can't do anything. I cannot transfer this current to the voltage because in the definition relation, I can't see that current here. So I am going to keep this one as it is. That means ICCVS equal to 0. So that's step 2. Let's go to step 3 now. We are going to transfer all the element voltages here to the node voltages. Remember the rule now. Rule is this. If there is an element, for example, okay, we start at I1, we keep it as it is, 1 over 2, V2. For the V2 is this 2 ohm resistor voltage. In terms of node voltages, VD1 minus VD2. Rule is this: beginning of the arrow of terminal node voltage minus arriving point node voltage, VD1 minus VD2. This is V2. So we're going to use this rule. We have seen this rule already, and this can be proved. So that's easy to write, equal to 0. And this one minus of this one is going to minus 2 VD1 minus VD2 plus 1 over 10 V3. V3 is this. So VD2 minus 0, because node voltage of the ground is 0. So that is directly VD2. Plus 1 over 5 VC. VC is the voltage of this element. In terms of node voltages, this voltage is equal VD2 minus VD3. VD2 minus VD3 is equal to 0. That's this one. This one minus of this one, so minus 1 over 5 VD2 minus VD3 minus 1 over 20 this fourth element voltage, that's the fourth element, the voltage of this equal to 1. Now we're going to use the rule. The origin of the arrow node voltage, this node voltage is 0, isn't it? 0 minus the arriving point node voltage, which is VD3. So you can directly write minus VD3, of course. Now that what this is fourth element voltage. This is V4 in terms of node voltages, we wrote, plus 1 over 2 fifth element voltage in terms of node voltages. So origin node voltage is VD3 and the arriving point node voltage is VD4 equal to 0. So this is what we have done. We have transferred this. And this one is going to be negative of this one, isn't it? Minus 1 over 5 VD3 minus VD4 plus ICCVS is equal to 0. That's step 3. Look at that step 3 now. The unknowns, that's I1 is one unknown, isn't it? That is independent voltage source current. VD1, VD2, VD3 are also unknowns, and ICCVS is also another unknown. So total number of unknowns here is 5 unknowns. How many equations do we have? So I said 5, it's not 5, it's 6, isn't it? 6 unknowns, 1, 2, 3, 4, 5. So I miss VD4, isn't it? That's VD4 is also included. So VD4 is this. So VD1, 2, 3, 4, 6, 7, 4, 5, 6. Altogether 6 unknowns. So we've got 4 equations, 6 unknowns, so that means 2 supplementary equations. 2 supplementary equations we are going to write. How we are going to write it? So look at this node voltages are the ones that we are expected to have. This method is node voltage method. So this is one of the source of the supplementary equation. This is another source of the supplementary equation. These are the ones for which definition relations we couldn't use. I couldn't use definition relation of this one. I couldn't use the definition relation of this one, which is this. So I will be using these elements definition relation in order to write the supplementary equation. How I am going to do it for this one? This is an independent voltage source of which voltage is known, isn't it? So this element voltage can be written in terms of node voltages. So since this is ground, so V1, it is VD1 equal to 1. This element voltage in terms of node voltage is equal to VD1 minus 0. I didn't write 0 here because the other terminal connected to the ground. So VD1 is equal to 40 volts. So that is the fifth equation, supplementary equation 1. That's sub 1. Sub 2, I will be writing supplementary equation 2 by using the definition relation of this dependent source, which is VCCVS equal 8 times IC. In this form, this is not a supplementary equation. This is the definition relation of the dependent source. So I've got to transfer this to supplementary equation. How I am going to do it? All the variables here that we see should be transferred in node voltages. Then I can say that this is a supplementary equation. Since this is an element voltage, this can be written as the node voltages. So here you are. This is VC, VS is the voltage between those two terminals. So since this is ground, this is equal directly VD4. So that is equal VD4. So clear that. Equal 8 times IC. Look at that IC. Is that current, isn't it? This is 5 ohm resistor current. 5 ohm resistance current can be written in terms of resistor voltage. So that is 1 over 5. This element voltage. This element voltage is equal VD2 minus VD3. VD2 minus VD3. So this is IC. So I use the definition relation. In the definition relation, I had the voltage here, that is VC, and I wrote this VC in terms of node voltages. So that is supplementary equation 2. So that is sub 2. So make it like that. So supplementary equation 1 is this, and the second one is this. So in here, in this equation, I've got node voltages. In here, I've got node voltage. So altogether, I've got 6 equations and 6 unknowns. So there is a unique solution. So after the calculation of these, solution of this equation is going to give us all these node voltages. One you know with node voltages, you can write the element voltages. If you know the element voltages, you can write the element current. So I'm not going to explain that. But what I should like to show you that in this area, you can directly write these resulting equations here. You don't have to do it step by step. Maybe at the beginning you could do it step by step, but once you get used to it, you can directly write this. Let me to write it. You should know that if you are using the node voltage method, you're writing Kirchhoff current law equations. You've got to start from the current equations. So write the first one. So I1, you cannot use the definition relation of these elements, so you can use I1 as it is. And I2, the sign is plus because it is coming out of the node. The current reference is coming out of the node. I put that plus here. So that current, I2 current, is equal 1 over 2 times this element voltage. 1 over 2 times this element voltage. What is this element voltage in terms of node voltages? VD1 minus VD2. VD1 minus VD2. So put in parentheses and clear this. So what I wrote here is that I2 is equal to 0. And the second one, so this one. Second one, so that's the negative of this one. I could easily write as 1 over 2 VD1 minus VD2. That is for this. Plus I3. I3 is the resistor current. So definition relation 1 over 10. This element voltage in terms of node voltages is equal to VD2 minus 0. I'm not going to write 0, so VD2. And this element current, the sign is plus. IC current is the definition relation 1 over 5 times is the voltage of this element. What is the voltage of this element in terms of node voltages is VD2 minus VD3. VD2 minus VD3 equal to 0. So finish that. And this one minus IC. IC we use that, so repeat that. 1 over 5 VD3 minus VD3, VD2 minus VD3, minus I4. I4 is this resistor current. So use the definition relation 1 over 20 times voltage of this element. Voltage of this element in terms of node voltages 0 minus VD3. That means minus VD3. So we wrote the current of this one and write the current of this one plus I5, it says, plus I5 is 1 over the definition relation 1 over 2. The voltage of this element in terms of node voltages, it is VD3 minus VD4 equal to 0. So I have done this. So I wrote this equation here. And the last one is negative of this one, minus 1 over 2 VD3 VD4 plus ICCVS is equal to 0. How to write the supplementary equation? So you're going to do this underneath here. That means you directly wrote all these 6 equations without using the step 1 and step 2. That makes it easier. So what we say, okay, once you found the node voltages, you can write all the elements voltages by using the node voltages. When you do this, that means when you write this equation and find the unknowns of these equations, it doesn't mean that you have finished the analysis, because analysis means find the element, all the elements current and voltages. In here, you haven't found them. So that means from those node voltages, we are going to find the element voltages. Easy. The rule is, if there is an element has got 2 terminals, that means has got 2 node voltages. You already calculated. According to the current reference, you can easily write this element voltage in terms of node voltages. You apply all this to the all elements. So node voltages transfer all the element voltages. Use the definition relations. You can get the currents of the elements. For those which you cannot use the definition relations, these elements currents are going to be calculated in these equations, because these are the unknowns. So these are already being calculated. So all the elements currents and voltages have been found, that means. So that's the end of the video, so stop recording.